Okay, so today we're going to talk about the GPT-3 paper, which I'm pretty sure all of you have heard about, but maybe didn't take time to actually read the paper. For a while, I hadn't read the paper, but I just, saw on the internet all the things that GPT-3 was able to do, and I was like mind blown. But then I was like, I'm going to force myself to read it by committing myself for the reading group. So the title of the paper is Language Models Are Few-Shot Learners. And basically, GPT-3 broke the internet over the past few months. I think it came out in May or something, or April. And so I gathered a few examples of the amazing things people claim GPT-3 can do. So this is one. Wait, can everyone see my screen actually?
Nope, not yet.
No.
Oh, God damn it. All right. All right. How about now? Can you see now?
Yeah.
Okay, great. So this is an example, one of the early examples that I saw, and I was like, what is happening? So what this guy built, which you can see in this little video, is a layout generator that you can specify with natural text. So this is for front-end web development. So basically, in this little input, he just describes what he wants to see, and then he clicks a button, generate, and then it basically generates HTML. And then you see sometimes it doesn't always get it right. So in this case, he's like fixing it a little bit, but then whoop, it just works. And here even asks for data. So it's layout and data, and it just works. So that's pretty cool. Like he has a bunch of, I'm not going to go through the whole video, but he has like a bunch of examples. Here's asking for 5 buttons. Let's see if that works. Yeah, so it's like pretty crazy. That's one example. Another example I saw is GPT-3 as a physician. So they basically ask a question like giving information about a case, and then what's the best diagnostic with like multiple choice, but also it's asking GPT-3 to motivate its choice. So it chooses the correct answer, and then it like gives a proper explanation as to why. So that's pretty amazing. Another one was someone took GPT-3 for a coding interview. So we're not going to go through the whole thing, but basically the interviewer is asking to write some Ruby code and then to more specifically reverse an array. And so so you see like GPT-3 is like, can I use a method that already exists? And it's like array.reverse. And then it like asks a few more questions. It doesn't actually get it correct. So you see at the end, the human is like, sorry, I don't think you passed this phone screen. But it's like the person who did this was still very impressed. So GPT-3 is not yet going to take your job, but maybe someday soon. Another example here is, converting natural language into Unix command. So it's asking to list files in a directory, and then it just like spits out the answer, move a file, etc., etc. I know at least some people on my team kind of fantasized about being able to do that a couple months ago. We're like, oh, it would be cool to have a converter from natural language to the Unix command, and now it's just like works out of the box. A final one that I thought was funny is GPT-3 as a therapist, where you see the prompt to GPT-3 was, we want to see a conversation between Nick and a brilliant, warm therapist named John. And so, Nick is like a little depressed, so I hate myself. And then John is like trying his best to make Nick feel good. Oh, that sounds really bad. You're not wasting your time. I'm glad you're here, etc. And it just like feels very natural and could actually be helpful. All right, so that's for like the kind of things GPT-3 has led to, but there's like a ton more. These are just a few quick examples that I gathered. So this is to motivate why this paper is important, I guess, but now we're going to go into the weeds as to what GPT-3 is. So the kind of very ambitious goal of GPT-3 is general intelligence, and you can kind of see GPT-3 as a strategy to get there. And so we'll go into the details of what that strategy is, basically. But GPT-3 is simply a language model, a giant language model that has 175 billion parameters, but it's still just a very simple language model. And it's, if you're familiar with GPT-2, is the same as GPT-2, just scaled up. Forgot how many parameters GPT-2 was, but much like orders of magnitude less than GPT-3. And it's basically the same thing. They tweaked a few things that I'm going to go over, but it hasn't changed since GPT-1, basically. It's like the same basic architecture. And the task is the language model task, which is just predicting the next word. So pretty simple. The one big innovation that GPT-3 introduces is the concept of in-context learning, which you can kind of paraphrase as multitask ability without fine-tuning. So that's the key part of GPT-3, and we'll go into that in details. And it also asks the question of whether to get closer to general intelligence, do we just need to scale up existing models, or do we need a real paradigm shift? And GPT-3's suggestion is that scaling up can get us closer. Doesn't claim that it will be the solution for general intelligence, but it's like evidence that it actually works pretty well to just scale up existing models. So again, the goal here was multitask ability, and traditionally, up until GPT-3, the way we typically approach the multitask ability problem is in two ways. Combining two ways. The first one is using transfer learning, and the second is to do multitask objectives. So combining these two is usually the way people have approached how to get to multitask ability. So transfer learning, the idea is to pre-train, usually on a self-supervised task with tons of data. And then as a second step, you have a fine-tuning step that usually relies on supervision, so labeled data. And this kind of approach, at least in text, in NLP, started off with Word2Vec around 2013, where the idea was to train word representations in as its own task, and then use those word embeddings in different tasks. And all the way to BERT in 2018, which was basically a way fancier version of Word2Vec in a way. So that's for transfer learning. So you use a ton of data for a self-supervised task, and then you transfer it for a task of interest. The big problem with this is that this self-supervised task, which in the case of BERT, for instance, was a masked language model, you need a ton of data, and then that means you need a high capacity model. And that means that when you use that super high capacity model with tons of parameters in the fine-tuning stage, you might risk overfitting, because typically fine-tuning requires supervised data, and typically you don't have that much supervised data. And so when you have a high capacity model applied on little data, comparatively speaking, you run the risk of overfitting. So that's like one downside of this approach. And then the second strategy, which is using multitask objectives to try to have a more general architecture. The big problem is that you're then dependent on having multiple pairs of data set and objective. So a very silly example that is close to what we do is for multitask objective is to do IC and NER with the same network, basically. But again, yeah, so the more multitasking you're adding to a network, the more you depend on those specialized data sets for each of those tasks of interest. So GPT-3 does not approach this problem that way. So now we're going to go over how GPT-3 wants to do this. Instead of trying to have multiple objectives, it's going to have one single training objective that is not customized or designed for any task in particular. So that's the language modeling task, which is just predicting the next word. And so here I took a quote out of the article because I thought that was like the key, basically the key insight of the article. So I'm just going to read it. Their bet is that a language model with sufficient capacity will begin to learn to infer and perform the task demonstrated in natural language sequences in order to better predict them, regardless of their method of procurement. So just to paraphrase this, the task, as I said, is to predict the next word. And the idea here is that in order to better predict the next word, GPT-3 is going to implicitly learn all the tasks that are demonstrated in all these examples that it sees in texts, whether it's in Wikipedia or in web forums and all that. So it's going to better predict the next word, it's going to have to actually understand the implicit tasks that are embedded in the text. So that's the key idea, I guess. And so for that, it needs to be general. It needs to have access to a ton of text where all these implicit tasks are demonstrated, basically. So that's why you need to pre-train at a very large scale so that you get an implicit, natural, broad distribution of tasks. And then the second key strategy of GPT-3 is to no longer do any fine-tuning. So as I was explaining before, the paradigm so far has been to pre-train on large corpus and then fine-tune on supervised data. And GPT-3 basically says that's not the way for general intelligence. General intelligence, you should be able to just take the model out of the box and apply it on a new task, and it should just work. You shouldn't have to like fine tune on that task. And so they replace fine tuning by what they call in-context learning, which you can also define as inference time learning, and we'll go over what that means. And I think this is the key reason why GPT-3 broke the internet, basically, because you don't have to like fine tuning and acquiring supervised data. That's a pretty costly thing to do. And so only a few people first can do that. That you need specialized knowledge to know how to create the architecture for fine-tuning. And then you need a lot of money to have the supervised data for your fine-tuning. And so it doesn't open up AI to the larger public, but GPT-3 doesn't require that. And so that's the reason why it has ushered a tremendous amount of creativity that we've seen on the internet, basically. Because people with little knowledge of deep learning can take GPT-3 and bend it to whatever task they want. And so you can kind of see GPT-3 in a way as a platform from which is going to sprout a bunch of apps, like an apps ecosystem. At least that's how I think it will become. But I thought that was pretty interesting. So what is in-context learning? So
Cedric?
Yeah.
So it's only using next word prediction and not masked word. Is that correct?
Yep, correct. Just next word. So typically, when you want to create a model for a specific task, the conditioning for that task is implemented at the architectural level. So you choose your architecture for that specific task. However, that's not how, for instance, humans do. Like a human, when you want to teach them a new task, you just explain them in natural language. Okay, so I want you to translate something to French. What does that mean? I'm going to give you a few examples, like this is a text in English, and this is the equivalent text in French. And you only need like one or two examples, and the person is like ready to go. You don't need to like upgrade your gradients in your head by absorbing hundreds of thousands of examples, and then you can do the task. No, that's not how human works. Like, plus, we don't like insert a new model in our heads every time we want to learn a new task. It's always the same. We use the same brain to do a bunch of different tasks, so we don't need to like have task-specific encoder or decoders, basically. Or another example of a natural way of defining a task is to tell someone, you answer the question, this is a document, this is the question, tell me the answer. So it's like, it should be very flexible, the way you achieve or you complete a task. So you can kind of see that as a general system should be able to condition on both input and task, whereas most of the architectures we're used to only condition on the input, and the task is kind of embedded in the architecture, or the conditioning for the task is the architecture itself. And then in-context learning means that the model will recognize the task as a sequence is fed to its forward pass at inference time. So if you look at the little diagram on the right, transformer decoder is basically the architecture for GPT-3. And you have this input sequence in green here, which defines the task and also potentially gives some examples. And then the prompt, you say, summarize this, and then it starts outputting things. But this is happening at inference time. So at inference time, you feed this green context window, which in the case of GPT-3 is of size 2048 tokens. So whatever you can fit in 2048 tokens is going to condition the language model, condition the output of the language model. And that's the in-context learning. So there's no fine-tuning whatsoever. You just you condition the output of the language model with that context window. And that's all there is to it. There's no fine-tuning whatsoever. So I'm going to give a few examples of that right now. So you can kind of see generalization of models as a continuum between fine-tuning all the way to zero shot. So fine-tuning is what we're used to. So here they take a little example in the paper for a translation, where they show examples in sentences in English and then their translation in French. And then they explain that traditionally you would show an example and then do a gradient update, show another example and then another gradient update, etc., etc., etc. So typically fine-tuning uses between 1,000 and 100,000 demonstrations. By demonstrations, they mean just labeled examples. And then the weights are adjusted. And as I was saying before, you might have a risk of overfitting because your model might have a high capacity. And so if you have a very high capacity model that you then fine-tune on 1,000 examples, let's say, you might run into overfitting. No matter how good your regularization is, that's always a risk. And then these three approaches are what GPT-3 does. So few shot means you're going to have only like a 10 to 100 demonstrations. So whatever can fit in 2048 tokens. So depending on the task, you might only be able to fit 10 examples in 2048 tokens, or more, or like 100. It's usually, they say in the paper, they usually can fit 10 to 100 examples in 2048 tokens. And the weights are not adjusted again. It's just conditioning the language model with that input. So it's very little data, and so you have less risk of overfitting. With 10 to 100 examples, there's like no way of overfitting at inference time. So this is the example here where they feed two different things. They feed a task description, so translate English to French, and then they give a few examples, and then they stop, cheese, and they're like, okay, what are you going to output now, language model? So here it's like the little arrow is the equivalent of summarize here, and then at 256 here, that's where the language model starts generating the translation for cheese. And then they try one shot where instead of having 1, 2, 3 examples like here, they only show one, and then based on one, like what's going to be. So it's like less conditioning. Then zero shot is they don't even show any example. They just have a natural language task description. So translate English to French, and then cheese, arrow, and then we'll see if it's able to translate to French. And like humans, that's how humans usually work, right? Like most people understand what translate English to French is. And so if you tell me cheese, then I can translate right away. I don't need to see that many examples. But for other tasks that we'll see examples of, humans also, they need a task description, but also like, what exactly does that mean? Can you show me examples? But they only need a few examples, like 1 or like 3, but you don't need like 100,000 basically. So that's the whole idea. Okay, let me do a quick time check.
One question, Cedric. This is Jack.
Yeah.
So when they're on your previous slide, when they're putting in the different lines, do they separate those, or is all just kind of one continuous stream of text? I
think it doesn't matter. You can either do a new line every time or not. I don't think it matters.
Gotcha.
Okay, so this chart, okay, larger models make increasingly efficient use of in-context information. Okay, yeah. So this in-context information, so the number of examples you can fit in this 2048 context window will generally improve the performance of GPT-3. So that's what this graph shows. So the colors indicate the size of the model. So they tried different versions of GPT-3, different levels of scaling up, basically. And then the x-axis is the number of examples in context. So k here is, so here k equals 3, here k equals 1, and here k equals 0. So this is the x-axis, and then the y-axis is the accuracy on the specific task. And the task here is you take a word and you like randomly remove letters from that word, and the task is like find those fix the word basically. And you see that so here at this level it's k equals 1, so it's one shot. Here it's a 0 shot, and then as you go that way you have like 10, so it's like a logarithmic scale on the x-axis. And so you see that bigger models improve, so the blue line, for instance, versus the orange or green line, improve accuracy a lot compared to smaller models when you provide more examples. So when you have more in-context information, you have like a bigger boost in accuracy with larger models. So this means in-context learning scales with the capacity of your model. So that's an interesting finding. Okay, so I'm going to go over the model architecture, but not spend too much time on it because it's not actually that novel compared to GPT-2 or even GPT. So here I showed the innovations between GPT, GPT-2, and GPT-3. GPT introduced the idea of transformer decoder, which basically, if you take the initial transformer paper, attention is all you need, and you have this famous diagram of the architecture. The transformer decoder idea is that you get rid of the encoder. So this part on the left of the architecture is the encoder, and the part on the right is the decoder. They just get rid of the encoder. And so in the decoder, they don't have this multi-head attention that attends to the encoder. So they get rid of that. And that's basically what transformer decoder is. It's this part of the architecture without this multi-head attention. So here on the right, this diagram is just an illustration of that transformer decoder. And so it relies on having a mask self-attention so that you cannot look ahead in the future and attend to words in the future. So it's like masked in that sense. GPT-2, the innovation, the two innovations that GPT-2 are not innovations, the two tweaks GPT-2 brought over GPT is fairly technical and not that important. No one seems to really spend that much time on these things, but they scale the weights of the residual layers with a different initialization factor. So there's, in the decoder architecture, there's like residual connections. So you see here this little arrow skips the multi-head attention. Anyway, it's just the way you scale, initialize, sorry, those skip connections, basically. It's not really that important, but just for thoroughness. And then the second thing GPT-2 introduced was pre-normalization. So you see here in the decoder, normalization happens after the multi-head attention. And I guess they just like moved it at the beginning instead. So not really that important, but worth mentioning. There's one innovation that GPT-3 brought, which was mostly for computation purposes. And I don't think it actually changes anything in terms of performance. They alternate dense and sparse transformer layers. So I'm going to go quickly over what that sparse transformer idea is right now. But again, it's not really for performance purposes. It doesn't it's not better. It's just computationally way more efficient. So that's why they did that. So what's the sparse transformer? That's where I had to go and read the paper about sparse transformer. So the idea is it's well illustrated with image data, actually. So some people applied transformer architecture to images. So it's the same idea as with text. Instead of 1D, it's 2D. So if you look at these examples, the black pixels here indicate the mask. And so this is it's kind of like an image language model, if you want. So you feed it some context, image pixel context, and then you ask to generate the next pixel. So that's the task, basically. And what they noticed is that attention was when you look at the query pixel you're interested in, which in this case would be the last one that is right before the black pixels, and you look at the attention heads when the query is that pixel, it's actually attending to only a few. It's not attending to all the previous pixels, basically. So, but it has the potential to attend to all the previous pixels. But for instance, so these different images, A, B, C, D, show the attention patterns at different layers of this image language model. So in this case, they have an image language model of transformer-based image language model of 128 layers. And so they represent the masked pixels as in black and the weight of attention as white pixels. So you can see that when we're querying, when the query is this last pixel, it's only attending to a few local pixels, for instance, for this layer. So this is for an attention head of a specific layer. So they notice patterns of attention. So in this case, it's local attention. In this case A. In the case B, they see a split of row-wise and column-wise attention. So you see here the attention is row-wise. In this case, for this attention head, the attention is column-wise. So you see patterns. In this case here, for layer C, they have global data-dependent attention. So you see that they're going to look at kind of maybe the contour of pixel images that depend on the data that you're looking at. But it's like a global attention pattern. And then here in D, it's like highly sparse attention heads where you can barely see which token it's paying, which pixel it's paying attention to. So basically, the key idea when you notice that is that we don't need to attend or offer the possibility to attend to all the previous pixels. You can just enforce structure on the attention patterns. So on the diagrams on the bottom here, they try to explain in the paper what that means. So on the left here is the full self-attention pattern. So these two squares here represent attention heads and images. In this case, it's 6 by 6 images. So when you're attending to this pixel, you're potentially, when you're querying this pixel, sorry, you're potentially attending to all these other previous pixels. So that's the dark blue is one attention head, the light blue is another attention head. And you can also visualize this in a connectivity matrix. So this just means that you roll out the image here. So it should be 36 pixels. Like the size here should be 36, but they don't put it to scale. So that means that if you're looking at the 36th pixel here, then you can attend to all these other pixels. And so the idea is to not do that, because that means you have a lot of matrix multiplications happening. And so instead they enforce structure. So in this case, they're like, oh, we're just going to attend to a few pixels right before the query pixel in this head. And then in this other head, we're going to do like the kind of column-wise, we're going to enforce the column-wise attention pattern. And so if you look at the connectivity matrix, this is what it looks like. And then same thing here. I'm spending way too much time on this, but the idea is that you're only attending to a few things, and so you save a lot of computation that way. Okay. Time check. 36 seconds. So throughout the paper, they present results with different capacity models. In particular, they have 8 different versions of GPT-3 spanning 3 orders of magnitude in size. So this is what this table summarizes. It goes from GPT-3 small all the way to like the real GPT-3, which is the 175 billion parameter one. And so the table just explains the differences. It's mostly number of parameters, number of layers. It goes from 12 to 96. The model is dimensionality of the model. And so I wasn't sure what that meant, so I kind of dug into that. And it just means that it's the size of the bottleneck layer in the feed-forward layer in the decoder block. So real quick, this is what this means. So you have in the decoder blocks, you have the masked self-attention, and then the output of that is fed into a feed-forward network. And the D model variable here is simply this dimension, in this case 768, which you compress the output of the feed-forward network onto that size. So that's why they call it a bottleneck layer. Again, not super important, but I like to understand the things that they put in tables. N heads is the number of heads, and you see you go from 12 to 96, pretty crazy. Then batch size, I think that's in terms of number of tokens. So you see the batch for the final GPT-3 is 3.2 million tokens for one batch, which is a little crazy too. This chart on the right is the performance in terms of validation loss with respect to compute. So the x-axis is the amount of compute. And then these lines, the color of the lines correspond to different versions of the model with different capacity, different numbers of parameters. And so you see that if you look at the point at which validation loss kind of plateaus, and you look at this plateau moment for a variety of model sizes, and you plot those, you realize that the validation loss or the performance of the model actually scales like a power law with respect to compute. So again, this is an indication that scaling up just works, basically. So that's pretty interesting. Okay, so what training data did they use for this? Pretty simple. They used Common Crawl with a little cleaning up there. They used WebText2, which is the second version of WebText, which they use for GPT-2. WebText is just they go on Reddit, and then they scrape Reddit for links, and then they go to those links, and then they scrape those links. And WebText2 is just a larger version of WebText1, I guess. And they only scrape like Reddit posts that have like a certain number of karma or whatever. They have the books, Corpora, 2 of them, and then Wikipedia. And then they kind of over or undersample these sources of training data. Yeah, so this column here just illustrates how much they oversample or undersample. And important to note that 93% of the tokens in the training data are in English. Okay, so a huge chunk of the.
Can I say one thing on the data? So there's a point that I thought was really fascinating as I was doing my Centurion research, which is that the amount of training data that they use to train is actually fairly small relative to other models. So GPT-3 is about 1,000 times bigger than XLMR, but it's about the same amount of training data. Or compared to T5, it's like 16 times bigger than T5, but 3 times less training data. So they're actually not using that much, relative to other models.
Yeah, that's a good point. Thanks, Jack. Okay, so a huge chunk of the paper is them evaluating GPT-3 on a bunch of things. So I learned a lot about a bunch of data sets that I'd never heard about, and lots of acronyms that I had to look up. There's basically 9 broad tasks, and then within each of those broad tasks, there's like a bunch of data sets. The kind of tasks they're looking at is completion tasks, closed book Q&A. So you cannot like look into a reference before answering the question. There's translation task, co-reference resolution. I think that's when you're matching a pronoun to a noun. There are common sense reasoning tasks like physical reasoning. There's reading comprehension task where you read a passage and then you're asked a question about it. And then there's superglue, which itself is like a bunch of tasks. It's become a benchmark in itself. And then there's natural language inference tasks. That's it mostly refers to entailment tasks. So you have a premise, and then you ask whether a given prompt contradicts the premise or is neutral with respect to the premise or confirms the premise or something like that. We'll see that in a second. And then they also came up with their own synthetic and qualitative tasks that are kind of fun too. So it's important to note that all these data sets have training data, but GPT-3 does not train or fine-tune on that data. So they compare themselves to a bunch of models that themselves actually leverage the training data for those tasks. So it's important to keep that in mind. Okay, so the completion tasks, you have Lambda, So all these are data set names: Lambda, LSWAG, and story close. So for Lambda, the idea is to predict the last word of a sentence with a paragraph of context. LSWAG is to pick the best ending to a story. And it was, the examples were chosen to be hard for a language model. And then story close, same idea. The idea is to select the correct ending. And so for all these tasks, they always compare themselves to the state of the art. And they show the performance of zero-shot GPT-3, one-shot GPT-3, and few-shot GPT-3. So the only difference between these are the the amount of conditioning you do in the context window for GPT-3. And you see that for Lambda is, I don't know if I'm pronouncing this right. It's basically beating the state of the art in terms of accuracy and also in terms of perplexity. It's not the case for story close or HelloSwag, but it's doing pretty decent job. So I'm not going to spend too much time on these performance tables because otherwise I will never finish. So I'm going to try to quickly go. The idea is to have a sense of the kind of tasks they've evaluated on. So here, for closed book, they had a series of natural questions, web questions, and trivia questions. And so the idea here is that you don't have any context. You just ask the question like, when did Darwin write his Origin of Species book? And then you just answer, but without having read a Wikipedia article about it or anything like that. So again, it's performing pretty decently with few shot. And what's interesting to point out is that there's a big improvement in performance as you increase the in-context learning, basically. So that means that the more context you provide, the better it performs, which means that the task is pretty out of distribution for GPT-3 out of the box. So you need to condition, the more you condition GPT-3, so the more you adjust, it's the data distribution it's expecting, the better it's performing. So that's interesting. So they do that a bunch for a bunch of those tasks. They look at how much in-context learning is happening. So some tasks need a lot of in-context learning and some tasks don't. All right, I'm just gonna keep going. So translation tasks. What's interesting here, so this chart illustrates on the x-axis the size of the model, and on the y-axis the performance in terms of blue scores. The color represents what language pair we're looking at, and then the dotted lines versus solid lines represent which direction. So dotted lines is from English, and solid lines are to English. So you see a pattern that when you're translating to English, it usually performs better than from English. That's because most of the training data is in English, and so it's a very strong English language model as opposed to, let's say a German language model. So when you're trying to generate German text, it's not going to perform as well as English text. But still, it's pretty, it's doing really, really well. For instance, from French to English, it's doing better than a supervised state-of-the-art translation system, which is pretty crazy. And again, no fine-tuning whatsoever. Co-reference resolution, again, so that's matching a pronoun to a noun. So here on the bottom left, I put an example of what that means in the gray box here. So an example is the trophy would not fit in the brown suitcase because it was too big. What is too big? What's it, basically? Is it the trophy or the brown suitcase? For us, it's pretty obvious, but maybe it's not that obvious for a language model. So that's the kind of task that co-reference resolution means. And you see here, so there's two versions of this data set. The Winograd is easy. Winogrande is basically more complicated. For the easy one, you see that there's not that much in-context learning. So the difference between zero shot and few shot is actually almost nothing. And it's also a little inconsistent. You see that the one shot performs better than the few shot. So basically no in-context learning here, whereas there's more in-context learning for the difficult task. So that's also pretty interesting. I'm going to skip this chart. It's always the same idea here. You have the capacity on the x-axis, accuracy, and then you have the few shot, zero shot, and one shot, and then you compare to state of the art. And you see that basically, I'm just going to go over this one and then skip the other ones. You see that there's more in-context learning happening when the capacity of the model is bigger. So that's the same insight that I highlighted at the beginning of the presentation. Common sense reasoning, these are tasks like physical interaction. So I give a little example here. So you have a prompt, you have some context that says to separate egg whites from the yolk using a water bottle, you should A, squeeze the water bottle and press it against the yolk, release, which creates suction and lifts the yolk, and then B is like a completely stupid answer, place the water bottle and press it against the yolk, keep pushing, which creates suction and lifts the yolk. So like that's not right, but we know that because we have common sense, but a language model might not have common sense. So it's these kinds of tasks that common sense reasoning tests for. And then other tasks in that category include grade science, third to ninth grade science exams, and elementary level science questions. So these are like actual exams that people take. And again, you see the various amounts of in-context learning depending on the task. And here for the physical interaction one, GPT-3 is doing especially well, which is kind of amazing. Okay, look at all these acronyms: COCA, quack, drops, quat, raise. Amazing. So these are just, you show a bunch of text and you're asked questions about that text. An interesting one I thought is the drop data set, where you're not only asked a question about the text, but also you're required to make operations on that text, on that text. So here they talk about it was sold for this much, it was estimated for this much, and then ask how many more was it sold than estimated for. And so it has to basically do a subtraction, which is like not obvious at all for a language model to do. And so here, it's way below state of the art. But if you compare to not state of the art, but the baselines these data sets were released with, GPT-3 sometimes beat the baselines these data sets were released with. So all these scores are F1 scores. RACE is like middle high school English exams in China. It's still pretty amazing that it's able to beat the baseline models for some of these. Okay, time check. Oof. Let's see. I'm gonna skip some of these because it's always the same story. Superglue is itself a bunch of tasks, from question answering to entailment tasks to common sense reasoning to fill in the blank task. And basically the key idea is that GPT-3 few shot beats the baseline. It's not the state of the art, but the baseline with BERT. Again, the baseline is fine-tuned on all this training data, and GPT-3 is not. So that's also pretty great. Maybe one important insight from Superglue is that GPT-3 does not do that well for entailment tasks, and we'll see an example in a second. Yeah, so entailment task is the same thing as natural language inference. So it's a 3-class classification problem. You have a premise and then a statement, and then you have to say whether one entails the other, contradicts, or is neutral. And for some reason, GPT-3 is not doing great at that. If you look at this chart, which looks at, again, the model capacity, the accuracy of a model capacity, like it's not doing great, maybe a little better with the huge GPT-3 with a few shot examples, but it's still like pretty well below the baselines, and let's not even talk about the state of the art. So they don't really explain why or have theories as to why it's not doing that great at entailment tasks, but it's interesting to note. The synthetic and qualitative tasks. So these are tasks that they made up for the purposes of this paper. For instance, they had arithmetic tasks where they just do what's 1 plus 2 or what's 23 plus 46. So they have two-digit addition, subtraction, 3 digits, 4 digits, 5 digits. And you see, so it's like more and more complicated, basically. And at first, it's like really bad for like really small models, but for like the final GPT-3, it's like doing amazing at, for instance, 2-digit addition and subtraction is like basically always correct. And if you look at this table here, which shows how much in-context learning is happening, when you compare the performance of 0-shot, 1-shot, and few-shot, you see that there's a good amount of in-context learning, which seems to indicate that this is really a new task that is out of distribution for GPT-3 and is like learning it on the fly, basically. Other examples of synthetic tasks are unscrambling scrambled words. And for some reason, one example of word scramble is reversing a word. So you see here, this is objects reversed. And so the task is to like understand that you need to reverse it. And it's doing really badly at that. Probably, I'm not really sure why, but they don't explain either. But interesting to note. Fun story, they tried GPT-3 on SAT, the analogy part of SAT, and it's actually beating college applicants. So that's kind of funny. News article generation, they take real world articles, they take the title and the, what do you call that, the subheading of the article, and then ask GPT-3 to generate the article, and then they show a bunch of humans, a bunch of these articles, and ask to distinguish what was GPT-3 authored versus human authored, and it's basically 50-50, they cannot tell. So that's kind of interesting. Okay, so these are that was for the evaluation. A big question that they try to address in the paper is GPT-3 just memorizing stuff? And their conclusion is that not really. And they have two arguments for that. The first one is that they don't see any evidence of overfitting the training data, which would be like kind of a requirement for if you want to claim that GPT-3 is memorizing. And the reason they say that is if they plot the amount of data that it's seeing, so that's the x-axis, and you plot the loss on the y-axis, and then they compare validation loss and training loss. The training loss is the dotted lines. If there was overfitting, you would see you would see these two lines between validation loss and training loss diverge, which they don't. So that's how they argue that first, GPT-3 is not overfitting the training data. And then the second thing they look at is data leakage between the tests, the test sets, and the training data. So they actually found a lot of contamination for many of those tasks that we just went through. And the way they did that is they looked at 13-gram overlaps between test data and training data. So they plotted that on the x-axis here, or it's the 1 minus that, so it's how clean it is. So if it's 100 here, it means it's like totally clean. If it's 0 here, it means it's like heavily contaminated. So they plotted that, and on the y-axis, they plotted the difference in performance on those tasks when they clean up the data set. So when they get rid of any 13-gram overlap in the test data. And so what they find is that basically the performance doesn't change that much when you clean up the data. So to them that means there's little evidence of memorization. Let's see. So for instance, for Pika, so that Pika here is the physical question task, physical reasoning question task. So it's not super clean, like almost a quarter of the data is contaminated. But what they tried is they took a model that was 25 times smaller, and they observed a similar degradation as with the full model. So the degradation was around, I don't know, like 3-4%. And they observed the same degradation, but if GPT-3 was memorizing, a smaller model should have a smaller degradation, and they don't observe that. So what their hypothesis is that this is due to model bias rather than memorization. Okay. Oh wow. Maybe I'll make it. So limitations and future research. Obviously, GPT-3 is very expensive to train. That's not great. Another limitation is that it's not bidirectional. So that goes back to Spencer's question about what's the task. The task is just to predict the next word. And so they cannot leverage the future. So there's no bidirectionality. And so that might be a limitation. The third limitation is that the training objective, which is next word prediction, is not the latest, shiniest thing. The latest, shiniest thing is denoising objectives. Denoising objective is basically just a generalization of mass language modeling, where you have access to both directions of the sequence, and one way of noising your data or creating noise is to like mask a word and like ask to guess it. But you can inject noise in a variety of ways, and some papers like BART or T5, I think, Jack knows more about this than me, use a variety of noise injection functions. So maybe this would be a better pre-training objective than just next word. Let's see. They also don't leverage any multimodal contextual information. So that just means, can we train text together with images? Maybe that'll lead to better real-world grounding. So that's also something they want to work on in the future. And then finally, you can kind of see in-context learning as a spectrum, which I've alluded to when I was explaining the amount of in-context learning between zero-shot to few-shot learning as you increase the number of examples you're conditioning GPT-3 with. So you can kind of see it as a spectrum that goes from GPT-3 is just recalling prior demonstrations. So that's basically rote memorization. And you can kind of see that in when it generates text, sometimes it's going to like use an expression that is just memorized because it's seen that expression in the text it was trained on, all the way to de novo learning. But you have intermediary steps where instead of just rote memorization, you can just see it as sampling from a distribution that is found both in training and testing. So it's very likely that GPT-3 has seen translation examples, for instance, in its training data. And it's at inference time, when you're asking it to translate and you give a few examples, it's like recalling that kind of distribution in the training data. And that's what the conditioning does to GPT-3, basically, to something slightly more abstract, where instead of sampling from the same distribution in training data at test time, it recognizes a general task pattern that it's seen in the training data. So in this case, it would be, for instance, recognizing a Q&A style. So that's matching a pattern that is seen in the training data, all the way to de novo learning. So an example task for that would be they make up a word. Like they ask a human, oh, come up with a random word and give me the definition, and then I'm going to ask GPT-3 to use it in the right context. So there's no way GPT-3 has seen that in its training data, So there's a lot of in-context learning happening there. We can be pretty confident of that. So you can kind of see GPT-3 as a spectrum from raw memorization to like really learning on the fly. That's basically it. I'm sorry, there's zero time for questions, but if people want to hang out a little more, I'm happy to discuss, or we can take it offline.